Welcome and hello. This is a video exercise on HEC HMS. And in this exercise, we are going to be dealing with the linear deficit and constant loss method. What we're going to be doing here is starting with a completed project, taking it apart, rebuilding it ourselves, and then running that linear deficit and constant loss method in a simulation, and then later in an optimization, and then comparing the results. All right, so what I have on my screen here is the HEC HMS tutorials and guides page, specifically the applying linear deficit and constant loss method page. I'll leave a link to this page in the description so you can go ahead and follow along if you'd like. I'm going to scroll down just a little bit. And before we get started, we need to download these files, the zip file, and then a spreadsheet. So go ahead and click the zip file, click download, wait for that to download, and then also click the spreadsheet. Okay, here's the download button for that. All right, so what I have is these two files. Let's see, if I open up the zip file, I have a project called LC Walnut Gulch, and here are the directories and files I expect to see inside of an HMS project, so that's good. I'm just going to go ahead and go up a level and then navigate to where I want to save that data. I'm just going to drag it over here into this directory on my computer, and then same with the Excel file. So I can close that, and we can delete that source data because what we have here is what we want. Next, what I want to do is open up this project in HMS. So I'm going to open up HMS, go File, Open, and then click the Browse button, then navigate to that project. All right, here it is, LC Walnut Gulch. So this .hms file here at the bottom is what I want. Click Select, and here is my project. It's all up and ready to go. What I like to do first is just look at what elements of the project I have, which is a basin model here. If I click on that, I've got two elements, a subbasin and a sink. It looks like everything is in place and geo-referenced. There's also a rain gauge here, as well as a discharge flow gauge, as shown on the map. We also have a meteorologic model that uses the interpolated precipitation method, control specifications, some time series data, and the terrain data file. Now, for most of this data, we're going to actually input this ourselves because sometimes just downloading a project like this and clicking the run button and then viewing the results is sort of takes away from the learning process. So what I've already done is saved some of the precipitation data. We have two different precipitation time series gauges, 83 and 384. So if you click on one of those, you can look at the data. You can expand to view the time window. And then here's the actual data itself. It's in millimeters. And then same is true with the other rain gauge. We can expand that and then look at the data here. There's also a graph of it. The other time series data set is a discharge gauge that's assigned to the sink element, which has the same control specification time window and then has discharge values in terms of meters cubed per second. So I'm going to be using this project as a guide to populate my own project, which will basically be the same information, but it helps me learn if I am inputting the data myself and understanding what I'm doing. One other thing I need to export besides this time series data set is the sub-basin element itself because it's geo-referenced, and using the interpolated precipitation method, it needs to know exactly the location of the subbasin, the boundary, and of course the location of the rain gauges. What I'm going to do is go up to GIS and then export layers. And then for layer type, I'll select subbasin. Next. Now this is the name of the shapefile that we're going to export. So for now, I'm just going to export it onto my desktop because I don't have my new project created yet. Basin 104.shp. Okay, and then finish. Okay, so it's confirming that that's saved, and it looks like it did over here on the side. I can see those files appeared over here. I'm just going to leave those files there for now. And I think that's really all I need to deal with the original project data. So I'm going to go ahead and click Save. Now what I want to do is actually create my own project. So I'm going to go File, New, and then here I'm going to give the project a name. I'm going to call my project exercise 25. You can call your project whatever you want, and then navigate to the directory where I want to save that exercise or that project. So I'll just put it here. Okay. And then click select. For units, we're going to use metric because that's what it was in the original, and click create. All right. I got a brand new project here. And the first thing to do is create a basin. I'll go up to the basin model manager, click new, and then give it a name. I'm going to try to preserve some of the same names that are used in the original, so Walnut Gulch. Okay, that looks good. Then I like to expand that Walnut Gulch basin model right here. Before I can import the sub-basin data, I need to actually put that in a better location than my desktop. So I navigated to the project itself, and then I'm going to put this in the GIS directory. It's a shapefile, so I think that's a good place for it. And then let's go ahead and import. So I'll go up to GIS and then imported geo-referenced elements. This is my new project. I'm just starting off here. Subbasins is the element type. Now I need to navigate to that GIS directory, which is right here. So click on the shapefile. Step 2 of 3, that looks good. We want to select the name. That's the only option to select here, and then click Finish. Okay, next we need to specify the coordinate system, and the source coordinate system I checked up was UTM, zone 12 north. So let's go ahead and select UTM, and then zone 12, and select. Okay, we'll click Set, and that sub-basin popped into place there. All right, the other hydrologic element that we need to add to the basin map is the sink. So I'm just going to do that manually. I'll click up on the sink tool here. I'll click off to the side. I'm going to name the sink Flume 104 and then create. And now I want to connect the subbasin to the sink named Flume 104. So I'll just single left click to select the basin and then right click, connect downstream. And then I'll single left click on the flume and that draws the line and makes the connection. So we'll click save to that. Okay, the next thing we need to do is enter the sub-basin data in the components editor. So with the sub-basin selected, now we can go ahead and look at the component data. And thank goodness some of the data already copied in for us, such as the area, the latitude, longitude, and so on. But some of this data we need to update as well. So using the data, the information from that original project we downloaded from the website, I'm going to go ahead and copy some of that data in here. All right, so discretization method is none. Canopy method is going to be simple canopy. Snow is none. Surface is none. The loss method is going to be linear, deficit, and constant. That is the name of the exercise, so I'm going to deliver for you on that. Transform method is Clark unit hydrograph. That's good. And then the base flow method is going to be none. All right, so let me go ahead and save those. Now we need to go ahead and specify the data for these different tabs, the canopy method, loss method, and transform method. The canopy method is using a simple canopy method. So these parameters here refer to the simple canopy method. The initial storage will be based on a percentage, which will be 0%. The crop coefficient is going to be 1.0, just as it is by default. That looks good. And then the max storage will also be 0, and this is in millimeters. Evapotranspiration is set to wet and dry periods, and then the uptake method is simple. So I'll click Save to that. All right, the next tab over is for the loss. This is the linear deficit and constant loss method. So these are the initial parameters we're going to set and then run for our simulation. And then these are also going to be the initial values of those same parameters when we run the optimization trial, which of course those values will change once the optimization runs. All right, so let's go ahead and set these. The initial deficit is set to 26 millimeters. Max deficit will be 48. Constant rate will be 15 millimeters per hour. That's saturated percolation rate. Decay factor and percent impervious will be the default values we're seeing here, -3 per hour and 0%. So I'll click Save. The last tab over we need to define is the transform method. We're using Clark unit hydrograph. So what we're going to use is method standard, time of concentration is 0.09, and then the storage coefficient is 0.06, and those are in units of hours. Time area method is default, and that's all we have to do here. Okay. So the peak discharge is definitely more sensitive to changes in the storage coefficient than in the time of concentration, at least according to my exercise 21. Go ahead and check that out. It's titled Clark unit hydrograph if you're interested. So those are the parameter data that we need to set for our subbasin. But the other hydrologic element we have is the sink down here, labeled Flume 104. There's nothing to input on the sink tab, but on this options tab, we need to specify the observed flow because this is going to be the target element for our optimization. So we need a target time series data set for that root mean squared error calculation to be minimized. Okay, I'm getting a little ahead of myself, but basically what we need to do is input some of that time series data that we grabbed from the original project. Now, before we enter time series data, it's actually going to be a little bit more efficient to create our controlled specification, which is what we're going to be using for our simulation and as well as the time series data sets. So I'm going to do that by going up to the Components menu, Control Specification Manager, New. Then I'm going to name this control specification the same thing it did in the original project, continuous from July 25 to July 30, create. Then we can close that. Now over here in the Watershed Explorer, I'm going to expand control specification, click on that control specification we just created, and then start entering the data in for the start and end date and time. So here is the start date at 1 p.m. And then the end date will be at midnight, July 30th. The time step is going to be 1 minute, so it doesn't get smaller than that. And then I'll go ahead and click Save. With that said, now we can go ahead and create our time series data sets. I mean, we could have done it before, but it will be a little quicker doing it this way. I'll show you why. Time series data manager. All right, we want 2 precipitation gauges and 1 discharge gauge. I'm going to do the discharge gauge first because I still need to remember to assign it to that sink named Flume 104. Discharge gauge will be my data type. I'll click new, and then I'll just go ahead and give it the name Flume 104 and create. Next, I need to create a couple of precipitation gauges. So I'll do that now. The first one will be rain gauge 83, and then click new. The second one will be rain gauge 384, create, and we're good there. All right, so now in our Watershed Explorer, we have a time series data directory with our precipitation gauges and our discharge gauge. I'll start by defining the data in the discharge gauge first. This is going to be manual entry. The units are going to be cubic meters per second. The time interval is going to be 1 minute. And then the latitude and longitude, we don't actually have to put in for the discharge gauge. Let me just go ahead and click the little plus button up by the discharge gauge up here. It gives me my time window. This is the default time window. It just gives you the first day of the year 2000. That's not what we want. But what I'm going to do is just create a new time window, and that'll allow me to delete this one. You can't delete the time window if there's only one. So I'm going to go up to the time series dataset, right click, create time window, and here comes the savings. I'm just going to, instead of entering the date, start and end date time over and over, I can just select this control specification that we already created, and then it just auto populates the start date and end time. So I'll click add to that and then close. And okay, cool. So it gave me a second record here for my discharge gauge time window. Here's the default time window it started me with. Here's the time window that I just created. So now I can right click and delete that default time window that I don't want. All right, so I have my tabs down here. Here's the time series gauge tab, time window tab, and now the graph and the table tabs. Okay, in Excel, I just copied the data from that original project for the discharge gauge and the 2 precipitation gauges. So here is the discharge gauge data here. It starts on the 1 o'clock p.m. of July 25th, 2010. I'm just going to copy all the records onto my clipboard there. So Control C, and then come back over here to HMS and then select the first record, right click, paste. Okay, yep. So the data popped into place there. I'll click Save. We can preview the data by clicking on this Graph tab here. And I know it's kind of hard to see, and this isn't the focus of the exercise, but there are 4 storms, and this is the discharge data here. So there's a storm at the very beginning and end, and then 2 larger storms in the middle. We're going to do the same thing by inputting the data for the precipitation gauge. So this is RG83. Again, I'm going to expand to see the time windows. It gives me this default time window that I don't want, but I'm going to go ahead and create a new time window and then use that control specification again. Create new time window. Here's the control specification and add, close. I'll do the same thing here with the other rain gauge. Let's create time window, control specification, and close. All right, now let me just delete those default time windows it gave me. I don't want. Okay, we're good there. Before we can enter the data, I need to also specify the time interval. So right now it's 15 minutes. I need to go ahead and change that to 1 minute and save. We'll do the same thing for the other rain gauge. I'll change that to 1 minute and save. Now let's go back to our first rain gauge and input the data. All right, so I'm going to come over here to Excel and then highlight the data. All right, so that's all the records there. More than 6,400 records because it's a 1 minute time step for about 4.5 days. All right, I'll come down to this record here, 101, and paste. And then let's see, save. And if yeah. So the last value pasted in exactly where I want on midnight of, at the end of the 29th. All right, that looks good. Let's do the same thing with the other precipitation rain gauge. I'll come back to Excel, grab that data, put it on my clipboard, Control C to copy, and then in HMS, I will right click and paste and save. All right, so before I forget, I want to come back to my sink here, the hydrologic element on the basin map. Click that, and then on Options tab for observed flow, I want to select Flume 104. That's the time series data set associated with the observed flow. So it's sort of serving as the perfect data set that we're trying to match. Before we can run a simulation, we still need to create a meteorologic model. So to do that, we'll go up to our components, Meteorologic Model Manager, New, and then we'll name this Interpolated. Create, we can close that. In the Watershed Explorer, I'll click on my Interpolated Meteorologic Model. Now, what we want to use down here in our components editor, we want to specify the unit system is metric. That's correct. No radiation. Precipitation will be interpolated precipitation, as the name suggests. And then for temperature, wind speed, pressure, and dew point, that will all be 0. Evapotranspiration, though, we're going to set this to monthly average right there. And then replace missing is going to be set to default. Okay, so one thing we need to do still is click on the Basins tab, change this from a no to a yes, save. And then in Basin 104 here, we can expand that. Click on monthly average to define the evapotranspiration. I've got that data saved in Excel because it came from the previous project. So we'll go ahead and click Save there. Now we're ready to create our simulation. I'll go up to the Compute menu and then Simulation Run Manager. Right now there's no simulations created, so we'll click New, and then we'll give the simulation a name, Continuous July 25th through 30th, Next. Now we only have one basin, so we'll select that. There's only one meteorologic model, we'll select that. There's only one control specification, so that's an easy choice. Now we're ready to select that simulation run and then run the simulation. Okay, it looks like there's an error somewhere. Oh, that's right. I need to specify the meteorologic data. All right, so if I go ahead and click on interpolated precipitation, I need to specify the interpolation method. So right now it says none, but I want to use inverse distance. This will tell HMS how much rain should fall on which areas of the map based on the location of the rain gauges, the time series data, and of course this inverse distance method. The source project also specifies a 10-kilometer radius of influence for both the gauges. So I'll just go ahead and select both gauges here, then type in a 10, and that's a little bit cut off. Okay, there's the 10. I don't think this is going to have any effect because this subbasin is only about 10 acres large. It's not very large at all. And then go ahead and click Save. All right, let's go ahead and run that simulation now and see if it works. Nope, there's still something up. Invalid coordinates, remove gauge from analysis. Let me see, did I specify the coordinates here? Oh, okay. I need to specify the latitude and longitude of the coordinates as well for these rain gauges. Duh, I just said that. I have that data saved. Here it is. This is the latitude and longitude for rain gauge 83. So we'll click Save to that. And then if I click on the other rain gauge, I have the latitude of 31.7425 north, and then longitude is 110.05353 west longitude. Save. Okay, so I think that's ready to go. Let's go ahead and run the simulation. Okay, great. It worked this time. Now I want to view the results from that simulation run. So to do so, I'll first click on the subbasin and we'll look at the graph. What we have here is 4 different precipitation events. So if I zoom in here, we have one event at the beginning, which has mostly loss with just a little tiny bit of runoff. If I scroll over to the second storm, that's right here. I got to zoom out a little bit. We have some infiltration loss, but then we have quite a bit of runoff as well. And then the third storm of the simulation is a day later, about the same size, maybe a little bit less. And then the final storm is the last few hours, which is right here, very little runoff. If we compare the actual observed data with this computed results that we have, I can do that by clicking on the sync right here, which has our associated observed flow data. And then I'll click the plot. In this plot, we don't have a hyetograph, it's only a hydrograph. But if I zoom in, I can now see that there's also a record for this black line here, which is the observed flow. And then the blue line here is our computed flow. So we don't have a very good match here, and these numbers are very small anyway. Let's go ahead and check out the second storm, which is quite a bit larger. Okay, so that's right here. I got to zoom out, zoom in right here. All right, so what we're seeing here is the black line is the observed data. That's what we're trying to match. And then blue line here is the hydrograph at that sync that's computed based on the model. So we have a little bit too much flow here. So our peak discharge is a little bit too high and our total volume is also a little bit too high. I'm going to go ahead and move over to the next storm right here. Again, it looks like in blue is our computed results, but we have, again, a little bit too high on the peak discharge and the total volume. But overall, it's a pretty good match. And then the final storm is at the very end of the simulation, and it's right down here, comparatively very small. Let me zoom in a little bit. Yeah, so the observed flow, it's fairly small, but then the computed results is even less, almost negligible. With the sync still highlighted here, I'm going to click on the summary table. And I can also access that summary table by going right click and then view results, graph, summary table, and time series data. I'm going to click on summary table. What we have here is a comparison with the computed results data up in this box right here. And then the box below has the observed data with some of the statistical parameters. So as you can see, our peak discharge is 0.9 and we wanted it to be 0.8. That's in units of meter cubed per second. I'll be the first to admit I'm not a big fan of one significant figure because this could be like a 0.94 and this could be a 0.75. And the zero point 0.9 could actually also be like a 0.85 and then a zero point 0.8 could actually be a 0.84. So it's kind of hard to gauge just how close these two peak discharges values are with just one significant figure. But that's how it is. Okay, the total volume here compares as 35.19 millimeters compared to our observed data, which is the target, and that's 26.73. So we're just a little bit over on peak discharge, and then we're quite a bit over on total volume. Also, I want to draw your attention to the statistical values down below: root mean square standard deviation, percent bias, and Nash-Sutcliffe. So Nash-Sutcliffe at 0.642 is a fairly good match, but not great. It's definitely something we can improve on. So those are the results from our simulation run. The next step is to create an optimization trial. So if we click on the compute tab, we can see that we only have simulation run right here. And then that folder will have our one simulation run. In the results, same thing. We have our simulation run with those results. Now we're going to create an optimization trial. To do so, I'll go up to the compute menu, optimization trial manager, and then click new. And then I'll give that a name right there. I'll click next. Now I select the basin and the meteorologic model, and it's been created. Now we need to define this data here. So some of it's already in place. We already selected the basin model, the MET model, and now for the start and end date time, this will be the same data as our control specification. And then instead of a time interval of 1 hour, we're going to select 1 minute. Okay, so I'll click save to that. I'm in the optimization trial tab here. So we also need to define the data here for search and objective. For search, we're going to use the simplex method. This is a deterministic method that accommodates 2 or more parameters. Max iterations of 100, we'll keep it that way. And then the tolerance is going to be 0.001, and we're going to be using absolute criterion. The next tab over is objectives. So what we want to do is minimize the discharge at flume 104, because this flume 104 here is what we have our observed flow data set already assigned to. The statistic will be root mean squared error, no transformation, and then the start and end date time is going to be the same data that we used before. So we'll click save to that. Next, we need to specify the parameters. These are going to be the 3 parameters that we saw in the loss method: initial deficit, maximum deficit, and the constant rate of infiltration. So length, and then length per time. Let me go click back on the compute tab of the Watershed Explorer. And on this optimization trial, I'm going to right click, add parameter. And we're actually going to need 3 parameters. So let me just do that 2 more times here for parameters 1, 2, and 3. I'll click on parameter 1, and now in the components editor, we can now define these 3 parameters. The element is always going to be basin 1. For this first parameter, we're going to use initial deficit right here, initial deficit. The initial value of 26 is reading from our subbasin data, so we'll just keep it right there. It will always be locked no, so keep that at no. And then the minimum and maximum values that were specified in the original project were 13 and 57. Okay, so that's good there. We'll go on to parameter 2. And in parameter 2, we'll select basin 104. This time the parameter is going to be maximum deficit. And then our initial value of 48 looks good. And then our minimum will be 36 and the maximum will be 72. So it's not a huge range for minimum and maximum. And after we look at our results, we'll make sure that the optimal value is not bumping up against either of these constraints. All right, the last parameter here is going to be, again, for basin 104. The parameter will be constant rate. There's that. All right, so we will just assume the same initial value because that's what we're using in the simulation run. So that's good. And then our min will be 11 millimeters per hour, and then the maximum will be 22 millimeters per hour. So fairly narrow range there, but that's fine. All right, so I'm going to go ahead and click save. And I think we're ready to run the optimization trial. So I'll select that. If it isn't already selected, go ahead and hit the compute. Now it's running through the different iterations. We set a maximum of 100, so it shouldn't go past that. Okay, so it looked like it converged at 20 iterations and 15 seconds of runtime there. That's good. I'm going to go ahead and click on the sink itself and then click on the plot. All right, so what we have is the same plot we saw before, but of course our computed data is going to be a little different. Let me zoom in here on the first storm. And this is interesting. So we still have the same observed flow, of course, but the computed flow isn't even showing up. So I guess it's 0. All right, so if I scroll over to the second storm, okay, so if I zoom in, now it looks like our peak value is now less than the peak value, but it looks like the volume is pretty close. In black is the observed flow, that's the target, and then in blue, this is the computed flow. If I zoom over to the next storm, this is the third storm. Okay, now we actually overestimate the peak flow and peak volume for this storm here compared to the observed value, which is in black. And then let's check out the last storm at the end of the simulation. And let me zoom in again. Yeah, so very little computed flow in blue here. And then here's the observed flow right here. If I look at the plot or the summary table, here it is. What we have is 0.8 meters cubed per second, which is the same as the peak discharge. The total volume is 25.35 millimeters of depth compared to 26.73. So that's much closer than we had before. And then looking at the statistical metrics to see how well that computed hydrograph at the sink compared to the observed data, all the metrics look a whole lot closer. To summarize the data that we're looking at here for the sink with the original simulation run and now the optimization trial, I've got the results summarized right here in an Excel spreadsheet. So we have the peak discharge and then the total volume and then the statistical metrics for the simulation trial and the optimization trial. With the simulation trial, we were off 12% on the peak discharge and 31% on the total volume. And then with the optimization trial, we were perfect for the peak discharge and the total volume, we were off just 5%. And most importantly, all the numbers, the statistical metrics have improved when using the optimization trial. Back to HMS, we can look at the results here in the results tab. If I click on the objective function summary, this is one of the more interesting ones, I think. These results are similar to what we just saw, except instead of percent difference, it's also giving us the absolute difference. And we also see the time to peak values right here. The next plot down is optimized parameters. And here we see the initial and final values or optimized values of those 3 different parameters. So we have the initial deficit, the maximum deficit, and the constant rate, starting at 26, 48, and 15. And the optimized values were 39, 41, and 12. So it's good to see that these optimized values are not bumping up against any of those minimum or maximum constraints we set for any of these 3 parameters. And you're welcome to check on any of the other plots here to show like how the different parameter values changed over the course of the evaluations. Of course, there were only 20 iterations, but there's sometimes more than one evaluation per iteration. Well, that was it for this exercise, investigating the linear deficit and constant loss method in HMS. We built a model from scratch using an existing model, ran a simulation, and then set up an optimization run, and then compared the results.